Good afternoon, everyone, first of all. So today we will talk about the tutorial number 3. So this is related with the synthesis and characterization and electronic properties of gold and the silver nanoparticles. So you people are, especially these students, are excited to synthesize the gold nanoparticles and silver nanoparticles with their own hand. Right, so I think this is also aligned with today's lecture. In the morning you have seen, in the yesterday's lecture you have also seen how the gold and silver nanoparticle can be synthesized in presence of different surfactants, how they are stabilized, how the color changes with the shape and the size, right? So now in today's hands-on experiment training, we will synthesize the gold and silver nanoparticles, and accordingly we can also study the electronic properties. We will study the band gap, how you can calculate the band gap of these nanomaterials through the different techniques. So if I am talking about the gold and silver nanoparticles, first of all, I think you people are familiar with this, that in the morning's lecture also you have studied that what you mean by the nanomaterials, that the size is below 100 nanometer. Broadly we classify those materials as the nanomaterials. So but the question is, why there is a limit of 100 nanometer? Why it's not above or less? So the basic answer to this is related with the, so see, in the first block, if you break it down further and further and further, you can see the surface to volume ratio will change, right? So the surface to volume ratio, it increases so much, surface area to volume ratio increases so much in case when the material is converted into the nano size. So in the nano range, like in 100 nanometers, some materials they, so this is a broad range, 100 nanometer is a broad range, but some materials they show the nanomaterial like properties, the specific properties at 50 nanometer, some show 80, but broadly materials they show different properties than bulk materials below 100 nanometers. So reason is the surface area to the volume ratio, it changes when the size decreases. So the simple example is like, if you talk about the solubility, again it's the surface to volume ratio. If you see the big cube of the sugar or the powdered sugar, then the powdered sugar will have more solubility. It is related with surface area to the volume ratio. So similarly in the nanomaterials, when the size decreases, then surface area per unit volume will also increase. So overall interaction of the material increases when the size changes. So the point is, although there are a number of nanomaterials that can be synthesized and reported in the last decade, but silver and the gold nanoparticles, they have a different class, they are class apart, and they have very significant applications not only in your biological field, but apart from this, these particles have great application in the electronics and the optical field also. So these have localized surface plasmon resonance. So because of surface plasmon resonance, this is the resonance occurring, which gives the unique optical properties. So when the size changes, the color of the nanoparticle suspension will also change. So that is because of the surface plasmon resonance. And because of these unique properties, these optical properties are unique, so they can be used in the biosensing as a biomarker, right? So biomarker means if you want to sense any bioanalyte in your human body, and imaging and other photothermal applications. So imaging is also related with the spectroscopy, because there is a different color with the different size. So this is more or less related with the optical property of the material. Right, so apart from this, there is gold and silver nanoparticle. If I am talking about the bulk material, bulk means which is more than 100 nanometer. The size of the material is more than 100 nanometer, we call it bulk. So if you see silver and gold nanoparticles, these are highly conductive, right? Bulk material is also highly conducting. And when the size changes to nano range, then obviously the conductivity will also enhance. right? So these gold and silver nanoparticles, so these have numerous application in the electrochemical field and the nano devices. And it's not like that we need a large concentration of the gold or the silver. Only a small percentage makes a huge difference, right? So like if I'm making a nano composite, right? So what do you mean by nano composite? It's a mixture of two materials or more than two materials in which one of the phase is in the nano range, right? If my composite contain 1% of nanomaterial, even then it will create a huge difference. So it's not always that we require a large amount of silver or gold, because you know the cost of the silver and gold is very high, right? So they have a chemical stability. Yes, the gold is, you know, the resistant. We wear the gold in the form of jewelry. Why? Because it's resistance to the atmosphere and all. Similarly, silver tarnish a bit, right? But otherwise, it is chemically, silver and gold, they are much stable as compared to the other metals. They are not that reactive. And moreover, when we synthesize the gold or silver nanoparticles, we can also stabilize these materials by surface coating, right? The surface properties can be changed by different coatings. So these further the stability of these materials can be changed. Next. So I have already discussed all the applications in environment science for metal for removal of the pollutant. So in catalysis, gold and silver catalyzed reactions are there, and in electronics, electrochemical, then optical devices, in biosensors and all that, and in biomedicine, right? So gold and silver, they can be used in the medicine. Apart from that, medicine, if you have seen in these days, we are using silver nanoparticles for antibacterial applications also. You have seen there is a washing machine or other microwaves with silver nanotechnology. So what is the silver nanotechnology? It's like antibacterial. You will not have a foul smell, or the bacterial growth will be lesser in that equipment, right? So these are the applications. Next. Now, as far as the synthesis is concerned, there are two pathways. Broadly, there are two pathways. The first one is like top-down approach. Like this is, if you look at the picture, this is the simplest way to explain. If you break a bigger size into the smaller one, that is a top-down approach. And in the morning's lecture, I think you have discussed, you have seen the discussion related to the top-down approach. So, but the disadvantages of the top-down approach is you will not get the uniform size and shape, right? So, uniform size and shape is the, you know, main problem in these. But yes, it has advantage. What is the advantage? That we can have a large amount of material at the same time, right? You can easily crush the material by ball mill or other techniques, and you will get the nanomaterial in a larger quantity. You can get the larger quantity, but the disadvantage is you will not get uniform size in the shape. So this is the disadvantage. But yes, if you want to have a larger amount and the properties are not that much size and shape dependent, you can use this method. But otherwise, the bottom up approach has more advantages as compared to the top down. So in the bottom up approach, the reaction is occurring at the atomic or molecular level. So once the reaction is occurring, then you will have the nucleation process, and in the nucleation process, after the nucleation, you will have a growth, and it will give you the nano clusters, and whatever you are kind crystals, nano clusters. So the molecule, the size of the molecule will enhance. So yes, one nano material or a nano cluster doesn't mean it is a single particle. It will be a combination of more than one nanomaterial depending upon the aggregation, right? So that is why it gives you different size and the shape. If there is only one nanoparticle, single atom, then it will be spherical, right? So why you are getting different shapes? Because once the nucleation is occurring, then the growth starts appearing. So after the completion of the growth, when the reaction completed, you will get the different size. You will get the different size. So this is also, you can say, this is a seed mediated growth. Once the seeding start, then the further growth will occur in that way. So in today's lecture you have seen that you can have variety of shapes of the material. So if I am saying the nanomaterials have different dimensions, so it can range from 0D to 3D, right? So no doubt 3D is not a nanomaterial, because all the three dimensions they are in the larger size. But yes, you can have 2D material in which only like nano ribbons, nanotubes, these are 2D materials. Quantum dots are there, right? 0D material in which all the dimensions they are in the nano range. Clear? So in this way, you can synthesize different material of different dimensions, different shape, different sizes. And you have seen in the morning that yes, you can control the direction of the nanomaterial synthesis also, right? Like if you block particular site, then you can increase the growth will only in one direction. So even you can not only the nano rods, you can have flower, star shape. So you have to optimize the procedure, and you can have different shape. So no doubt the surfactant or the capping agent has a huge role in different size and the shapes. So these are the different methods: the ball milling, laser ablation. So these are the top-down approach methods. Then your sol gel, microchemical, hydrochemical, polyol synthesis, then your condensation method. So these all methods, they are from the bottom-up approach, where the atomic level the reaction is occurring at the atomic or molecular level, and they will continuously giving you the bulk material, right? Mark करें यहाँ. For example, you have a gold, right? So now this gold nanoparticle, once it is formed, right, it can continue to grow like this. It can give you the spherical nanoparticle. And if there is some capping agent, like I am adding this cysteine, this is a amino acid, you know this cysteine. So if this is capped on the gold surface, like gold nanoparticle is there, and there are, if we are using water as a solvent, then we have surface hydroxyl group. So sometimes when we run the IR of the material, you will get the peak of OH group also. So now this OH group is there. So this can give you surface functionalization. Right? So now you can see there is a charged species at the surface. Now the other gold nanoparticle, definitely it will go in this direction. How it will combine now? So you will have interactions over here. This is, so gold nanoparticles, they will combine like this, have a little bit space, and they will orient like this, right? So these interactions will bind the nanoparticle and leads to the growth of the nanoparticles in a particular direction, or they can be spherical also. But this is a growth phase, which is because of the electrostatic interactions. Next is, okay, so we have already discussed this. So applications I have already told you. Now we are coming to the synthesis part, the fabrication of the silver nanoparticles. So now in case of the silver nanoparticle synthesis, we will use the silver nitrate, right? So we will give you the solution of the silver nitrate. We have already prepared the solution. So you need to have 0.25 millimole of silver nitrate, and you know how to calculate the molar solution, right? You know in the first lecture that you have to find out number of moles and how much amount of the volume of the solvent you will use, dissolve, and that will give you the molar solution. Number of moles dissolved per liter of solvent, that is the molarity, right? So here you will have 0.25 millimole of silver nitrate and 0.25 millimole of SDS. And what is SDS? Sodium dodecyl sulfate, right? It's an ionic surfactant that will be used in this case to stabilize the nanoparticle suspension, so that the particles can stay stable for the longer period of time. And next one is 0.3 milliliter of cold 0.1 molar sodium borohydride. Now what is the role of sodium borohydride in this case? You have a silver in plus form. In silver nitrate, silver is in plus form, right? So from silver plus to silver you need what? You need a reducing agent. So what is reduction? Gain of electrons. So sodium borohydride will act as a reducing agent. So you need a reducing agent, and the silver plus it will gain 1 electron and it will convert into reduced form silver, right? So now this is a reducing agent, and the product is, you can see this yellow color, it's a mustard yellow color, and this is the yellow brownish mustard yellow color of the silver nanoparticle. So you can see the silver is not always silver. Now it seems golden, right? So this now when you talk about the color coding, then you will say, okay, yellow color of this concentration of nanoparticle, it is yellow. But if you are talking about the bulk, then it will give you silver, right, in chemist language. So next one is the gold nanoparticle synthesis. Now we will use the auric chloride. This is another salt in which we use instead of the silver nitrate, we are using the auric chloride. This is the salt of the gold. So again the same procedure will be there, concentration will be same. Sodium borohydride will again use as a reducing agent, SDS will be there to stabilize the nanoparticle. So instead of SDS you can use the other stabilizing agent. Sodium citrate is there. You can use the other surfactants, the natural surfactants you can use, the saponins, like they are the Rita is there, right? They have saponins as a natural surfactant. So there are a number of other surfactants, Gemini surfactants are there, right? So you can use other surfactant also, but this is a basic technique for the synthesis that we are telling you, and further you can look into the literature and you can explore the reaction, and you can further apply your brain and ideas, and you can modify it. So in this case you will see they appear ruby red color, right? So the color of the nanoparticles will be ruby red color. So I think you have seen in today's slide also, in Dr. Bakshi's slide, the ruby red color is because of the spherical nanoparticles, right? So once the particle size is increased, then it slowly it shifts to the bluish color. So see, the gold is changing so much colors depending upon the size, right? So this is not the new technology. Basically earlier there were no techniques for studying the size of the nanomaterial. We have now sophisticated equipment like electron microscope and XRD and all that, where you can see the size of the nanomaterial. But otherwise the nano exists in the nature quite longer period of time. So if you see the old buildings of certain church or other buildings, so on the glass they have a stained glass. So those stained glass have the suspension of the nanomaterial, because these suspensions are giving different colors. So the painting, the stained glass was made up of different colors of the nanomaterial, like silver and gold and the copper. So different colors are obtained at different concentration and stabilizing agent, right? So that is already existing earlier. If we add this amount in the gold, then we can get this color, and that was used in the painting and all that. But at that time there was no instrument to measure the size and all that. That's why it was not known. And the second thing is, these materials are photoactive, right? So when the glass was there and sunlight was coming, in the presence of sunlight, these materials act, and the bacteria or the other species which are present in that area, because that is a public area, so they have advantage that they are also getting killed. right? So they are photoactive materials. Silver is antibacterial in nature, right? You know that. Copper is also showing these kind of properties. So now you can synthesize gold and silver nanoparticle by these two techniques. Two different salts will be used in this case. The simple procedure is there. Different color is there. You can visually detect the formation easily from the color, right? This is the best characterization technique. You have the sensory system, you can view through the eyes, and apart from this you can check it through the UV spectroscopy. I am giving the different techniques that can be used for their characterization. Today we will use only UV visible spectroscopy, but I will show you the data, how you interpret the data, XRD, TEM, UV and FTIR. So first of all, in case this is the XRD, and the powder, in this case we use the powder XRD, not the X-ray crystallography. Here we use the powder method. And you know what are the X-rays? The rays which are generated from the target molecule when the high speed electrons, they are bombarding on it. So the transition of the electron is occurring from higher energy shell to the lower energy shell, and they generate the X-rays. So the first Nobel Prize was given for the discovery of X-ray in 1901 by to the Rontgen. And this is one of the very important discovery of the science, because the X-rays can pass through the soft tissues but not through the bones. So without surgery, doctors can view the any bone fracture and all the injuries, right? So not only it is the X-rays are important from our material characterization, but it has biomedical application, lots of biomedical applications. So now the X-ray diffraction method is used here to study the lattice parameters, like you have seen in the morning 111, 101. So what were those? Those were the lattice parameters. So those lattice parameters can be analyzed through the X-ray diffraction method, the phase, the crystallite size. By Debye-Scheurer equation, you can find out the size of nanomaterial through the XR. Okay, so through TEM you can visually see through the TEM micrograph, but yes, through the XRD you can also see the size of the nanomaterial. So this is the XRD of the gold nanoparticle. You can see we have different planes, 111, 200, 220. So this is already reported, and these planes are at different angles. Diffraction peaks are at different diffraction angle. The different angles are there, 38, 44 and 64. So now the point is that how I can check that my gold nanoparticle is formed. So there is JCPDS data, where the crystallographic data is always there, and there is particular JCPDS number, file number, that belongs to that particular crystal, and we normally compare our data with that reported data. So when we compare, we found that these peaks belongs to particularly gold or silver or iron, whatever the metal is there, we can easily compare it with the reported data, right? Next, so this one is for the silver. You can see we have a prominent peak again at 111, 200 and 220. Next. Okay, now UV visible spectroscopy. Today you will see the UV visible spectrophotometer, and you will analyze your synthesized silver and gold nanoparticles by the UV spectroscopy. So now you can see next. This is the UV spectra, UV visible spectra of the gold nanoparticles. So we have plotted this against the wavelength and the absorbance. The absorbance that is shown by our nanomaterials. So we will give you the cuvette. You will add the solution into the cuvette, and then you will run the sample into the UV spectrophotometer, and you will find out this graph. I will show you in the lab course. So you can see there is wavelength 520 nanometer. So you know this 520 nanometer belongs to the gold nanoparticle. So you have one peak only, not the two peaks. So you have seen that if the different shape is there, like rods are there or wires are there, then you will have second, again a second peak will be there. But here you will, if you are looking at this spectra, you have one peak only. It shows the particles, they are more or less spherical, or you can say rough surface spherical, right? Next. So this is for the silver nanoparticle. You will have a peak at 400 nanometer in our synthesized method, right? If you use the another method, it may be possible that if you have a different shape, it may be possible you will get another peak also. And yes, with the change in color, the wavelength will also change. Remember this thing, right? So what is the visible range? It is in visible range or not?
Yes, yes.
What is the visible range? 3600 angstrom to 7200 angstrom, right? So this is in the visible range. That is why you are able to see the color, right? 520 and this one at 400 something. Next. So next is the transmission electron microscopy. So here again, that transmission electron microscopy, the fast moving the electrons, they bombarded on the surface of the sample. And why it is called transmission? Because the electrons, they can pass through and you will get the clear image of the substance. Apart from then the SEM microscopy, where there is different secondary electrons, auger electrons, where the electrons are reflected and you get the image from the reflected electrons, we call it SEM. And when the electrons are transmitted through the sample, we call it transmission electron microscopy. So here if you want to see the size, shape, morphology, and if it is having a layered structure, if it has a coating, you can easily find out through the transmission electron microscopy. So this is the TEM image of the nanoparticle. You can see they are more or less spherical in shape, but you can also see they are not agglomerated. They have a space. Why they have a space? Now you can see why they have a space. So right, so if it is coated with some surfactant or some material which provide them stability, so that material is between these two nanomaterials. That is why you can see the space. Otherwise, what will happen? They all will agglomerate and it will give you a bulk size. This is again of the silver nanoparticles, TEM image of the silver nanoparticles. These are from our papers. This is again FTIR of the gold nanoparticles. So now in this case, this is around, if you talk about the nanomaterial, they have a surface functionalization. So in this case, you have a functionalization of sodium dodecyl sulfate. So if it is purely, metal oxide or the metal, then you will not have any peak or this bands in this particular area from 2000, 3000, right? It will be below 1000 if it is metal oxide or the metals. But in this case, all these peaks are because of the surface coating with the organic moiety. You have a sodium dodecyl sulfate. So you can see that there are different CH2 bending, different type of vibrations are there, then sulfate is there. So these peaks related to the surface coating of the surfactants which have organic moieties, and that is why you have the peaks of all these, and it shows that coating is there. Similarly, again in this case. So next one is the electronic properties. So why they show different electronic properties? They have better electrical conductivity. Now the conductivity, it also depends upon the band gap. Band gap is the gap of the energy between the conduction and the valence band, right? So if it varies, then the band gap will also vary. So if the size of the nanoparticle change, the band gap will also change, right? So the electrical properties, they are more or less based upon the band gap. And again, the surface plasmon resonance, they will decide the optical properties. So sometimes the optical properties can be aligned with the electrical output, and you can sense the material, and this technique is used in the biosensing of the material. So obviously I have told that silver and gold, they have a better chemical stability as compared to the other metals, although they are costly. Because of this particular feature, they are used in the various nanomaterial synthesis. And yes, quantum size effect, if the size can be reduced below 10 nanometer, we can say they have a quantum effects also. Catalytic properties and charge transfer is also possible in case of these. So I have already told you this band gap. So you can see the valence band and the conduction band. If you decrease the size, then this will show a semiconductor like behavior. The band gap will change. Next. So yes, you can find out the band gap through the TOS equation. So this TOS plot can be derived from the UV spectra. From the UV spectra, you can find out there is a Lambert-Beer law, right? So from the Lambert-Beer law, you can find the absorption coefficient, and using that absorption coefficient, you can find out the band gap very easily. So Eg is the band gap, H nu is the energy for the transition, A is the absorption, and your alpha is the absorption coefficient, and N is the transition. So when we draw the plot for this TOS plot, you can extrapolate this, and you can find out the value of Eg is 1.83 in this gold, and in this our silver nanoparticle it is 2.79 electron. So yes, you can find out the size from the XRD plot also. So in case of the XRD, there is a Debye-Scherrer equation. So you can find out the size through Debye-Scherrer equation also. The K is the constant, Scherrer constant, the value is 0.9. And lambda, this is the wavelength of the target. Normally we use copper in this case, 1.54 Angston is the value. So copper is normally used as a target, but if you change the target, the wavelength can change. But mostly the nanomaterial, when we characterize a nanomaterial, they use the copper K alpha as a source or as a target of the X-rays. So next is the beta, and then is the cos theta. So what is the beta? Beta is the full width half maxima. So if you have the plot of the, like this is the X-ray plot. So what is this? This one is full width. This one is full width, and the half. This one is the half of this peak, and this half will give you full width half maxima. And the value of this full width half maxima will be this cos theta, the angle which is there, angle of diffraction which is there, and from this you can find out the crystallite size of the nanometer by using the XRD. You can compare the data of the XRD with your TEM analysis also. So you can compare both and can find out what is the average crystallite size of your nanometer. Okay, so now I am concluding that today you will synthesize. I have given you the instructions and the brief introduction about the silver and gold nanoparticles. What are the possible method of their synthesis? How you can manipulate the different methodologies according to your need, and what are the different characterization techniques. So apart from these, there are other characterization techniques, but these are the basic ones which are really necessary. You can have other information also related to these nanomaterials. So UV you can run today, and you will see where the absorption will be there in your particular synthesized nanomaterials. Okay, so again top plots you can draw by yourself. and from that UV data you can draw the top plot and you can find out what is the band gap of your material, right? So if you have any query, okay. So shall we start with the hands-on? Okay. I will show you the demo that how you synthesize the silver nanoparticle and then gold nanoparticle. So we have already synthesized, you can see the silver nanoparticles, and you can see this is quite stable, and they are not settling. The sizes it is quality manufactured out this and out. This one is where is your? This one is gold. Now this sounds a little bit more, but because of the sample, so we have three different solutions. What are the three different solutions? We have silver nitrate, we have sodium sulfate as a capping agent, and third one is a reducing agent, which is sodium chloride. So first one is we have the silver nitrate. So how much is 10 ml? And what is the concentration? 0.25. And this one is SPH. So this is the stabilizing agent. And this is again 10 ml. Now we have the reducing agent. Sodium chloride, and how much is 0.1. Nanoparticles are very simple technique, right? So now we are formed. Silver is not always silver. So now we will have the second one, the gold nanoparticles. So after this we will conduct the UV spectroscopy, and I will show you the images, the absorption that we will do. Now we have the aurichloride. This is again aurichloride. We are using in the lower concentration. How much is concentration? 0.25 mole. Millimole, not mole, millimole. 1 gram is 25,000. What is the cost? Now we can multiply 1,7. Sodium sulfate, the capping agent, or you can say stabilizer. And then the last is the reducing agent. Rubical, exactly. So now you can synthesize these materials like this. And further, first to synthesize, in the meantime, you will do the UV spectroscopy, and you can give the sample one by one, and the UV spectroscopy will also be conducted. After taking the UV data, you can have a top plot, and through the top plot you can find out the band gap of your, right? You can use this suspension in nanocomposite synthesis also, right? You can add the bulk material to your these nanomaterials and to convert into nano composites. So you can have different applications like you can use it in photocatalysis, and obviously the sensing is also there, and as a catalyst also, a variety of applications are there. So as I already told you in the morning, you can read the research papers and you can get more ideas, you can think about it. You can start now one by one. You can keep your samples in the vials, right? So these nanomaterials which you synthesize today, these will be used in your last tutorial number 5. So you have to keep these nanomaterials. You don't need to throw it or waste it because silver and these are costly ones. So these suspensions will be used in the last day. So in the last day, like silver and gold, they are heavy metals, transition metals. So if your sample has similar kind of other heavy metals, we will synthesize the iron oxide nanoparticle in your next tutorial. So iron oxide nanoparticles, they will be functionalized or they will be stabilized by different surfactant, diamine surfactant that you have synthesized yesterday. So that diamine surfactant will be used for synthesis of iron oxide in tutorial number 4, and that iron oxide will be used in tutorial number 5 for the extraction of these silver or the gold. As you will see, when you will add iron oxide to these suspension, the gold will be absorbed from the iron oxide and the solution will become clear. With the magnet, you can remove the iron oxide from the bottle and you can see the polluted is removed. So now this silver and gold is acting as a polluted or the heavy. Okay?
ये सीटी वाला स्लो जा
Now you can see this one is a ruby red because the concentration of the surfactant was a little bit more. So I have diluted it now. So this one is ruby red and this one is bluish. UV करते हैं. UV के बाद
अच्छा है। हाँ लोग सेंटर में
पूछ ले।
यहाँ पे नहीं था वो कल था
नहीं अभी भी
अच्छा वो उधर वो इसका भी ड्राइवर का भी
हाँ हाँ
जगदीश
करके दिखा तो दिया रिजल्ट आता है
क्या दिखा
इस लाइन में है क्लोराइड, अभी क्लोराइड होगा इस लाइन में, याद नहीं होगा तो वैसे मैंने हाथ से पढ़े तो ये होता है सोच तो थोड़ा रिस्की है। लैपटॉप पर भी चेक करेंगे तो आपको टिक शो कर देगी कि कहाँ कहाँ की टिक आ रही है। थोड़ा सा लेफ्ट में घूम सकते हैं। चेक की करा ठीक है ना, तो आपकी कितने तारीख 516 ठीक है ना? तो क्या हो गया इसका मतलब आपके गोल्ड नैनो पार्टिकल्स ठीक है। ओके, तो वापस सिल्वर वाले को करते हैं। चेक करो, क्या करो, निकालो कीबोर्ड निकालो। इसको अपने में रखो।
एक एक करके ग्रुप वाइज ही आओ ना आप, एक करके
एक ग्रुप
कुछ टीचर्स भी है ना।
आप लोग आ जा रहे हैं हाँ थोड़ा और थोड़ा रेंज करो ना। अब से स्टार्ट करते हैं तो नीचे देखो क्या क्या है कैपेसिटी आपकी स्टार्टिंग है 800 से एंड टू टेम्परेचर हाई लिमिट एंड इंटरवल 1 अब स्टार्ट करते हैं
ਤੇ ਉਸ ਤੋਂ ਬਾਅਦ ਜਿਹੜੇ ਆ ਜਿਹੜੇ ਵੀ ਕਿਰਾਏ ਤੋਂ ਵੀ ਸੈਕਸ਼ਨ ਹੋ ਗਿਆ ਚਾਈਨੀਜ਼ ਨੂੰ ਵਾਪਸ ਚਲੇ ਗਏ ਉਹਨਾਂ ਨੂੰ ਬੈਟਰ ਸੈਲਰੀ ਹੋਤੀ ਹੈ ਉਹਨਾਂ ਨੇ ਮੈਕਸਿਮਮ ਚਾਈਨੀਜ਼ ਜਿੰਨਾ ਟਾਈਮ ਸੀ ਉਹਨਾਂ ਨੇ ਮੈਕਸਿਮਮ
वाला है ना 400 के अराउंड ही जा रहा है
So you have exercised? You can take that.
आपकी ना इंटेंसिटी ज़्यादा होगी कंसल्टेशन ज़्यादा होगी ना इसलिए इंटेंसिटी ज़्यादा होगी और इंटेंसिटी है वो बनने के आसपास है तो उसमें एरर के चांसेस कम हैं।
You can put your group number. You can add the group number and simultaneously the UV is also there. You can see the peak at around 400 is there, right? So this belongs to the silver nanoparticle. Silver nanoparticle. Screen पे कर बस ठीक है. So now you can see the UV plot. Hurry up, come here. So now this is the UV spectrophotometer. You can see this equipment. So we are adding the cuvette full of your sample. So cuvette is added of this silver nanoparticle. We have prepared this silver nanoparticle, yellow colored solution. So now the sample is kept inside this UV visible spectrophotometer, and the analysis, the UV plot of the sample is here. The peak is occurring at around 395 nanometer, closer to 400 nanometer. So this is the peak. So if there is a shift in the peak, either it can be bathochromic, or it can be red shift, or it can be blue shift, right? So if it is toward the higher wavelength, we call it red shift. If it is toward lower, it is called blue shift. So as the size changes, the shift can occur from this side to this side. So now you can carry out your own spectra. Now this one is particularly for the silver. So next we will run for the gold nanoparticle. You can take the picture, and from these values you can draw the top plot. From the Lambert equation, you can find out the value of alpha, the absorption coefficient, and using the absorption coefficient you will derive the top plot, and from top plot you will get the band. So you will do the calculations now after this UV spectra. So every group will carried out this UV spectra for his or her own sample. So this one is the UV cuvette. You can see this is the UV cuvette. This is okay. So you can put the sample in this. You have the black sample. So already we have the sample, black sample, which is containing water. So it is there, and now this is a test sample. So now the gold one. So you can get back the sample, because there is no effect of this UV on your sample. It will not decompose, right? So this will not disintegrate your sample. You can use it again. So you can get the sample back from the cuvette in your vial. इधर भी कर दो बच्चों, विक्रांत को कर दो स्टूडेंट्स. So now you can see, you will get the data. can take the image of your plot also. So 516, I have told you 520 nanometer. So this is approximately same 516 nanometer. Earlier it was 516 nanometer. So now you can see this broadband is there. So why you get broadband in the UV spectrum? Why not the sharp one? Have you seen all UV spectra? In the other one also. So UV spectroscopy is electronic spectroscopy. So here the transition of electron is occurring from one energy level to the another energy level. So the point is each electronic level has a number of another levels, vibrational energy level, rotational energy level, right? So the transition of the electron can occur from one vibrational to other, one rotational to other. So large number of transitions are there in the this electron spectroscopy, UV spectroscopy. That is why each transition contribute and you get a band, broad band in the spectrum, right? Because each and every transition is contributing. So transition of lower energy in this area and higher energy in this area. So everything is contributing, which gives a broad band in the UV spectrum. So now you can see the peak is easily visible around 516 nanometer. So now it is confirmed you have synthesized the gold nanoparticle. Other group has the other previous spectra was of silver nanoparticle, which was around 396, right? So now the next group will also carried out, and in the meantime you will plot the top plot, and from that you can calculate the band match. So carry on one by one, group wise you can draw the spectra.
प्रॉपर अमाउंट में ही जाना है, ज़्यादा तो वो पब्लिश कर देगा फिर आप डेटा ऑप्टिमाइज कर
all students are getting their value around 568. So it means like it's versatile, like giving the same value again, accurate. Okay. नीचे वाले लैब में यूवी में कभी भी ऊपर वाले लैब में फ्लोरो करने जाओ ना, कभी 10 कम दिखा देगा, कभी ज़्यादा दिखा देगा। उसमें प्रॉब्लम वो फास्ट है ना। आपका सिल्वर का 400 वो 395 के अराउंड आएगा, सबका तो इतना ही आ रहा है। Now click on this check key after the spectra list. Check key. See, it's 390. Okay, you can click picture. Take out the payment and take your sample and then gold 560. ओके, कोई कैमरा चलता है ना, फोटो मशीन का भी है ना, किसी और मशीन का भी होता है। Anyone want to try? Plan?
Have you calculated the tau value? So you can keep the sample and store it, or you can submit it to our team. So on the last tutorial you will use these samples for the removal of this silver and the gold from the aqua solution. So now we will remove the heavy metal by means of the iron oxide. So this one is 395 and 560. Submit the sample. Yes, ma'am. Take the sample. Okay. Okay, you can keep it in the report. So you have the same value? Yes, 569, 400 or 393. So you can give the sample in your area. What is the value of UV? 390 for the silver nanoparticle and around 560 for the gold one. So the color is perfect. We give it the bluish or black, right? It means we are the stable. Now can you see the suspended particle? What are these suspended particles? These are the fibers of tissue. Right? So that is why when we are working in the material, we in this place of the figure. And you see that figure with the tissue paper. So how many groups or everyone has completed? Yes. So now I am winding up. So all the groups have completely synthesized the silver and the gold nanoparticles. Yes. Everybody. So we have two different samples, one of the silver and other of the gold. Can you show me the samples? So you can take the data from the UV spectrophotometer and using that data you can draw the top lot. We have the original software, and through this software you can put the values and you can draw the top lot, and further you can get the band. So these are the silver and your gold nanoparticles. So please preserve these in your Almira. So day after tomorrow, when you have the 5th tutorial, you will use these nanoparticles for the separation of these nanoparticles from the aqueous layer, right, from the aqueous solution by using the iron oxide nanoparticles. So here the silver and the gold nanoparticles, they will act as a pollutant, or you can say the heavy metal in water. So you can clear the water. Similarly, here in this in future's experiment, you can purify the water, remove the contaminants from the water with the use of nanoparticles, iron oxide, surface active iron oxide nanoparticles. And similarly, you can use these nanoparticles for the other applications, for the biosensing, optical sensors, electrochemical sensing, or you can synthesize the nanocomposites. So you can read more research papers, get more ideas for their applications. Okay. So keep this sample and store it. We will use it. Okay. So now the synthesis you have done, the characterization you have done with the UV spectroscopy. Take the data, and now you can plot the top lot and get the value of the band. Okay, so now the tutorial is finished. You have completely understood how the compound iron, silver and gold nanoparticles, they are formed by the wet chemical synthesis, by solution synthesis, and how you can characterize easily in your lab. Further, if you want to analyze for the XRD or you by TEM, then you have to go for that characterization, and you can get the size of the nanoparticles by transmission electron microscope. And there are other techniques also where you, for example, if you are synthesizing iron oxide nanoparticle, then for a magnetic material you have to find their magnetic properties. So BSM analysis or squared analysis can be carried out to study the magnetic properties of those materials. So that is not for the silver and gold nanoparticle. That is for magnetic material, like iron oxide is there, or copper ferrite is there, any ferrite, copper, cobalt, nickel ferrite, or you can have other materials like perovskite material like bismuth ferrite, BiFeO3 type compound. There are different variety of magnetic materials. Iron oxide is not the only one, right? That we will do in the next lectures and tutorial. So thank you. If you have any questions.